All right, so we have a cyclic quadrilateral with AB equal to AB. Let's see. Put point C over here, so that point D is here. So AB is equal to AB. I think I'm going to hide that circle. All right. That looks more like a G. M and N are on CD and BC, so that DM plus BN is equal to MN. That's a tricky criterion. How would I do that? How would I draw that? Probably just have to guess at it. Let me do it like this. So basically, I want it so that these circles are tangent, basically. So let's see, they gotta just barely touch, and then that would do it. That's hard. How do I make it so that they just touch? That doesn't look too good. Let's see. It's tricky. You know, tell you what, I'm just going to, because yeah, I know the program's not perfect, so I'm just going to call this the tangency point H. All right, so pretend H is the point of tangency there. So I'm going to draw, so let's call this M. So DM plus BN is MN. Okay. Prove that the circumcenter of AMN belongs to the segment AC. That doesn't, let's see. Oh, that looks true. So we're saying E should lie on AC. Yes. That's interesting. All right. How do we use this information? I'll be right back, guys. All right, I'm back. Okay, so we want to show the circumcenter of AMN belongs to AC. Are EM and EN tangent? Let's see. No, I don't think EM and EN are necessarily tangent. You try drawing things a little bit differently. Whoops, I hid those points. Wait. Yeah, okay. So let's see, how do we use that condition? The circumcenter of AMN belongs to AC. So we could try to show angle NAC is equal to NAE. It's one way to do it. Or NCE is equal to NCA. So I wonder if CH is like the radical axis of those two circles. And I haven't used the fact yet that AB is equal to AD, but that basically means that CA is the angle bisector of BCD, right? So we want to show CE bisects that angle. This kind of reminds me a little of the broken chord theorem, or Archimedes theorem, if any of you know it. So what would that mean? That would mean that ENCM is cyclic, right? Because if CE is an angle bisector, and we also know EN is equal to EM, then that means the angle bisector of this meets the perpendicular bisector of MN. So let's see. So yeah, that would mean ENMC is cyclic. So can we prove that? So that's just an angle chase? Let's see. I wonder if ADMH is a kite. That looks true. Are those both like kites? So is AH always equal to AD? Yeah, it looks like DHNB is. It looks like A. Is that obvious? Now I'm not sure if that actually is true. Maybe it's just the way I drew it. Let's see. I wonder if that's just how I drew it. Let's try something like this. This is so tricky. Yeah, no, But it looks like AB equals AH at least, and AN, well, no, because then it looks like, yeah, it looks like A is the circumcenter of BDH. Is that obvious? Well, I feel like I might be missing something obvious here. So angle ANB, so basically I want to show that A is like the excenter of triangle MNC. Is that true? Let's see. Yeah, I want to show A is the excenter of triangle MNC. I feel like it's just true. So what do we know about the excenter? So we want to show A is the excenter of MNC. Is this some kind of in-center, excenter lemma? So what is the, I wonder if this intersection point here is the in-center. What is the in-center of MNC? We want to show that this point is the in-center. So if we could show En equals EF equals EM, that would solve it. I see a bunch of equivalencies here. Oh, but that's true. Wait a sec. I think it's, so we have EF is equal to En is equal to EM. Can we show that F is the in-center? By the way, are you still there, Urjong?
Yeah, I'm here.
All right, thanks.
Is there anybody else?
No, I don't think so right now.
Okay. I had an idea. What if we take a point X on DC such that AN is equal to AX?
AN is equal to AX. Let me see. Oh, I think that would be like, we want to show that's where the other intersection point of the circle is, right? So like that would be point X. We want to prove that this point is point X basically, right?
Yeah.
Okay. Yeah, is that an... Let's see. I might as well label that one too. Yeah, what if we like let A prime be the X center? I'm just trying to think here.
How are you trying to show that circumcenter of AMN belongs to the segment AC?
Yeah, so here's kind of my strategy. So there's a couple different equivalencies I have in mind, but basically we know that AB is equal to AD, right? So that's the same as showing that, so we know CA bisects angle BCD. So if we can show CE bisects angle BCD, that would solve the problem, right?
Yeah.
And it turns out that there's a bunch of equivalent things, but it's equivalent to showing that A is the excenter of MNC. If we can show A is the excenter of MNC, that would solve the problem. Also, I'm trying to think the other ones I have in mind. If we can show AB is equal to AH, that would solve the problem. But yeah, I wonder, like what if I did this? Like, what if I draw a perpendicular from A to BC? Like, I want to show that that's the X circle. And I know that Bn is equal to NH. Let's see. So I have that NK plus ML is NM. So NK plus ML is, I think I might have it.
Is MB equal to ML?
Is MB, or I'm sorry, did you say ML?
Yeah.
I don't think ME is equal to ML.
MB is equal to ML.
No. But if the problem were true, BK would equal to DL. BK would be equal to DL. And oh, NB, I'm sorry. I think that would be true if the problem were true or correct. NB would be equal to ML. Oh no, I thought it was true. But KB and DL, I think should be, yeah. Okay, I think I have an idea. I'm just trying to figure out how to express it, how to write it up. Let's see. So basically, yeah, I kind of drew the X circle here. If we can show the X circle is centered at, if we can show that A prime, if we can show that A is actually the center of this X circle, then that would solve the problem. So suppose we don't already know that A is the center of it, and we want to show A is the center. We know that BK is equal to DL. We know that AK, we know that, so I think, yeah, I think I have a way of writing this. It's just a little awkward. So what if I draw some point A prime? What if I let A prime be the actual center of the X circle? And I want to show that A prime is equal to A, but we know that BK is equal to DL. We know that A prime K is equal to A prime L. And we know, yeah, okay, so I'll try to write it out like this. Let me see if this makes sense to you. Hide these two. Whoops. All right. Let me hide point H also. So we can say let A prime be the center of the X circle omega of triangle MNC. Let omega be tangent to Cn and Cm at K and L. So then we want to show A prime equals A. But we have Mn is equal to Nk plus Ml, and it's also equal to dm plus bn. So that means that bk is equal to bl. And we also have A prime k is equal to al. Okay. And so that means that A prime kb is congruent to A prime lb, and A prime b is equal to A prime b. And then we also know that AB is equal to AB. And so, so AA prime lies on the perpendicular bisector of BD. Is it obvious from this information that A equals A prime? You kind of see what I'm doing?
Yeah, I can see it. It's a very nice solution.
But I don't see how to finish it. Do you see like is it obvious to you that A and A prime have to be the same?
Yeah, since A prime B is equal to A prime D.
Mm-hmm. Yeah, so A prime B is equal to A prime D, and AB is equal to AD. But why does that mean A has to be the same as A prime? I don't see it myself. So yeah, I can show A prime AB is congruent to A prime AD if those 2 points were different. Oh, and we also know A prime LKCK is cyclic. I think that might be enough to finish off the problem.
Yeah, now we have point A prime fixed.
So do you see how to finish it off? I don't see it yet myself.
Can we prove that angle ABD is equal to A prime BD?
Maybe. Let's see.
That would finish.
Yeah. So what else? Let's see. So if A prime is the excenter, then A prime lies on, oh, I think I have an idea here. I can show that C, yeah, okay, I think this finishes it off. So A prime is the excenter. And then so C, A, and A prime are collinear. And then not only that, both of them have to lie on the perpendicular bisector of BD.
This means they are in the same point.
Yes. So that means A is A prime. And then basically we've solved the problem because actually now I'm trying to think. So I had the idea, but how does that finish it? I know I remembered it from before. Basically, once we know that A equals A prime is the excenter, I said it earlier in the video. How does that finish it? Okay, so basically we wanted to show that CA, so we know CA is an angle bisector. We want to show CE is an angle bisector. Which was the same. How did I do it? I know I said it earlier in the video. Somehow I'm all confused now. Okay, so I'm gonna let, yeah, I think it's because I made this other point. So if we call this point P right here, the other point of tangency of the F circle. Now we know that A, K, and P is a kite, right? So basically I can delete A prime. So oh, I think I had it. I think, yeah. So basically, it's because yeah, when I was talking about the problem earlier, I had this other point here. What was I saying earlier? My memory is so bad. So we have AB is equal to AO is equal to AD, right? Yeah. So basically we have a kites here. Yeah, so I wanted to show ENCM was cyclic, right? What was my plan to do that? I wanted to show angle ENM, ENB is equal to angle EMC. Let's see. Okay, so yeah, since En is equal to Em, if we can show E lies on the angle bisector, if we can show ENCM is cyclic, then that would mean CE would be an angle bisector, and EMCN is cyclic. That, I'm trying to think where I went from there.
Did you give a reason for it before? I think I heard you, but I forgot.
So yeah, if I can show EMCN is cyclic, that would solve it. And somehow I went from that to showing that A was the excenter. I just can't remember how I did that. I know I had an idea. So I think we want to show ENJ is congruent to triangle EMI. Yeah. Okay, let's see. So NA is an angle bisector. MA is an angle bisector. Make sure that EA, this is also, CA is also an angle bisector. Was it the in-center, excenter lemma? Maybe. So, I mean, basically I think it's just the in-center, excenter lemma. Yeah, isn't it? Because basically, if you just look at triangle MNC, A is the excenter, then we could draw the in-center, and they both lie on a circle. Yeah, so basically, like if we hid point E, I was way overthinking this pretty much, but basically if we hide point E for a second, if you just look at triangle CMN, the in-center and the excenter lie on a circle passing through M and N, right? And the center is the midpoint of that. So this is just the in-center, excenter lemma. You see what I mean?
Yeah, I can see. Insert the excenter lemma with respect to triangle CMN.
Yeah. And that solves it. Yeah, somehow, yeah, I was just forgetting what I did, but yeah, it's actually very simple. All right, let's try at least one more problem before I finish. I'm just going to draw an E here. That solves the problem. All right. Oh, this one looked kind of interesting. Okay, so the triangle ABC, where AB is greater than AC. All right. Then we have a tangent to the circumcircle at A. AB has to be the greater one. A circle centered at A and radius AC cuts AB at point D. And it cuts the line at points E and F. C and E are in the same half plane with respect to AB. Oh, whoops. No, we want that's E and that's F. Prove that the line DE passes through the incenter of ABC. That's kind of interesting. So I'm gonna label the incenter. We want to show that ED and I'll call it I are collinear. Let's see. This looks like such a simple problem, doesn't it?
This looks like an easy angle chase.
Yeah. I wonder if CI and yeah, if CI and G are collinear. No.
Can we compute angle ADE?
ADE.
Yeah.
So ADE is the same as AED, which is FED, which is maybe.
What angle were you asking? AED, right?
Yes. Hi, Sai. Thanks for joining.
Hi. Well,
yeah, this looks like a nice, so AED is equal to, let's see. So AI is perpendicular to CD, right? Because the centers of two circles.
well, another thing, angle CAE, I think, is angle B, and because of alternate angle segment theorem, CAE.
angle CAE is angle 8 is ABC, right?
Yeah, angle B.
All right, so CAE is angle B, which is the same as angle CGA. Okay, so angle CGA is angle B. We want to show angle IGA is also angle B, right? And I'm sorry, we want to show
Oh.
EI and D are collinear. So
ADE is actually computable if you take angle DAE, that is angle A plus angle B, right? Yeah, the
yeah,
A
you're
plus angle
right.
B, and we can find by angle sum property.
So angle ADE and AED are both half of angle C, which is angle ACI. So CI, let's see. So AECI is cyclic, I think. Wait, if I can show it. Let me check that. I think that would solve. Yeah, we have to show AEC and I are cyclic. It looks like, yeah, this doesn't necessarily concur. So ADE is half an angle C, and ACI is half of angle C. ADE equals ACI. Ah, that's it. It's that simple. All right, so yeah, John figured it out. We don't need any cyclic quadrilaterals. So I'm going to type it up. Feel like that gave us a little confidence boost there that it's we got it fast enough. Okay, so oh, it's not 180 minus, it's just half of that. All right. And then ACI is equal to ADI. So we have so that means, so if since ADE is equal to ADI, DE passes through I. All right. I like it. Let's go on to the next one. I didn't LaTeX this problem yet, but you can still beat it. All right, so ABC is a triangle where AC is greater than AB. Let X be on line AB so that BX is equal to AC. It's a little bit tricky. So BX, okay, so I'm gonna have to use a compass for this one. There's a compass tool, so we want BX is equal to AC. And CY is equal to AB. All right, and XY intersects the perpendicular bisector of BC at P. And we want to show angle BPC plus angle BAC is 180 degrees. All right. So D is the midpoint of BC. I'm going to just hide a bunch of stuff. You hide AC. Okay, so we want to show BPC plus BAC is 180. That's the same as saying BPC is XAC, right?
We could reflect point B.
Reflect point P across BC.
Yeah, we prove that it's a cyclic quadrilateral and
Yeah, I see what you're saying. Or I wonder if we could reflect A, and that might be easier because then we'd have a parallelogram. I'm going to reflect point A instead. And then if that doesn't get us too far, I'll reflect point P. But the reason why I like reflecting A is because, oh, P might, let me see. So AB is, oh no, it's not what I thought. But no, what I'll do is I'll reflect A across point D so that we have a parallelogram. So basically, and then yeah, we still want to find a cyclic quadrilateral, but now we have a parallelogram, right? Is PY, yeah, so I think we want to show that PY and A prime are collinear.
Sorry, why is it a parallelogram?
Oh, I define point A prime so that A prime C is a parallelogram. I just did it by definition. I constructed it for myself.
Got it.
And so then, kind of like you said, we want to show BPCA prime is cyclic, right? And we know CY is equal to CA prime. And we know BX is equal to BA prime. So it's like we have two isosceles triangles, and they have the same vertex angle. I think I might have a solution, actually. Yeah. P. So is AY the angle? I think AY is the angle bisector. Yeah, I'm just thinking how to state this. Is A prime BD isosceles? I don't think necessarily. No, because you could have it like that, for example. But A prime BX is isosceles and A prime CY is isosceles. And I think we should be able to use that to show that those two triangles are somehow similar isosceles triangles. In fact, they are similar isosceles triangles, but I think we should be able to use that to show that A prime Y and X are collinear. Yeah, so basically we know that A prime CY is isosceles. We know that A prime BX is isosceles. And yeah, we can use an angle chase to show that A prime Y and X are collinear. So I'm going to start writing this up.
Actually, correct. Triangle XBA dash is similar to triangle YCA dash because since as you said, ABA dash C is a parallelogram, so opposite angles of parallelogram has to be equal. So angle ABA dash is probably equal to angle ACA dash, which is equal to YCA dash.
Yes. So I'm going to write out what you just said. So first, let A prime be such that A be A prime C is a parallelogram. All right. So then so actually we weren't given that A prime, AD and A prime are collinear, but that follows. Okay. And then we have all right. And now I'm going to use these two facts. So they're similar isosceles triangles. So I'm going to write that out. But I'm going to use it to show that A prime, Y, and X are collinear. So here's how I'm going to do it. C. Okay, and then we can use the same argument to show that angle CA prime Y and so since BA prime X is half of that angle and CA prime Y is half of that angle, they add up to BA prime C, and so that means A prime Y and X are collinear. So I'll write it out like this. Okay. And then once we know that, so P is both the intersection of the angle bisector from A prime with the perpendicular bisector of BC. So that means P has to be the midpoint of arc BC of the circumcircle. So that means we can draw that circle, and then that finishes off the problem because it's going to write out the last step. All right. I'm going to see if we can squeeze in one more problem. Usually I make it around 3 hours. So if you have to, all right, see you, or John, have a good one. Let's try to fit in this one last problem. So K and L are the X circles of triangle ABC. Yeah, I don't know of a fast way to draw X circles.
Hey Michael, how did you learn this GeoGebra stuff? Because I'm also trying to figure out how to draw these lines and make circles.
Oh, so you can see the tools here, right? I kind of just learned it myself, but like the line tool, you can just draw a line between 2 points, perpendicular. You just pick a point in a line. Like, is there anything I'm doing that I guess doesn't seem intuitive or seems confusing?
No.
Yeah, I think you just play around with it a little bit, and then eventually you get used to it. Okay, so I'm going to draw the X circles. Um, all right. So they call it B1 and C1. M and N are the reflections of B and C about B1 and C1. This is yeah, let me shrink the diagram a little bit. So if I reflect B about B1 and C about C1, and I call it M and N. Oh no, B1 and C1 are the midpoints, my bad. So that's K, L, and then this is B1, and then this is C1. And so basically we have a parallelogram, right? Because we're reflecting B across B1 and C across C1. All right. So basically that means that yeah, like we have a bunch of stuff. So yeah, this is a parallelogram, this is a parallelogram. These two are the midpoints. So what do we want to show? We want to show K, we'll call that M and N. We want to show KM and LN meet on BC. That's interesting. That's kind of tricky. KM and LN, we want to show they meet on BC. Let's see.
Wait a second. M is reflected with respect to what?
M is a reflection of B over B1. So it's a reflection of B over the midpoint of AC. And so
Oh, I actually thought it's the point of it's the tangent point of AC. It's actually the midpoint.
oh, you thought B1 might be the tangent to C point.
Yeah.
Yeah. That's kind of interesting. Yeah, I wonder if we can like, so one way that I do these problems sometimes is like, I could let KM meet it at a point and try to show like FC is equal to F prime C. Or like if I let KM meet at a point F and I let LN meet at point F prime, then I want to show F is equal to F prime.
Yeah, so we're trying to prove N, L, and F collinear. So I wonder if we could prove angle NL, NLF, NLF, and do some bunch of angle changing to prove that NLF is in fact a straight line.
Yeah, I think that's a good idea. Let's see if we can do that. So we know CL is an angle bisector of ACB.
MN is parallel to BC, right?
Yeah, MN is parallel to BC. So yeah, we have two parallelograms actually. So BAMC is a parallelogram and CANB is also a parallelogram.
Right.
In fact, I could probably just hide. Well, actually, yeah, I don't think I want to hide it. But
Yeah, so MN is actually twice the size of BC.
yes, MN is twice the size of BC. That is correct. So L, A, and K are collinear.
L, A, and K.
Yes. So L is the center of this circle, K is the center of this circle.
Ah, yeah, I got you.
So really, if we want to show, I wonder if we could use Menelaus, because if L, N, and F were collinear, then by Menelaus, we would
Yeah.
have Km over Kf is equal to FL over Ln. In fact, it's the same as showing NK is parallel to ML. If we can show NK is parallel to ML, that would solve the problem.
MK is parallel to NL.
Yeah,
Um,
or NK and ML. So that and that, if we can show those are parallel. They don't look parallel though.
they don't look parallel.
No. What was I thinking?
Which triangle are you trying to take using this Menelaus theorem?
So basically like triangle LKF
Ah,
and then
makes
MN.
sense.
So we want to show K, I see why it's not parallel necessarily. We want to show KM over KF. So basically if we reflect M across K, then we want to show a parallelism, I think. So basically it's like, if we do that, then we want to show M prime N is parallel to ML. I think, no, what was I thinking? That over that. Yeah, we want to show M prime N is parallel to KL. Yeah, those do look parallel. We can show that. Yeah. So KL is the line joining the two centers of the circle. But I think it's true. Can we show M? Can we show M prime N is 90 degrees? That's the question.
M prime N.
Or can we show MKA is 90 degrees?
Yeah, any single one will work.
K. Is it obvious that MKA is 90 degrees? I think that would solve the problem. Yeah, it looks like it shouldn't be hard to show that MKA is 90 degrees. I can hear a beat in the background.
What?
Is there some kind
A
of,
bee?
or is there not a bee, but like
No, there's a clock ticking right there. So
a clock? All right. So yeah, M prime KA, we want to show that that's 90 degrees. How do we do that? So it feels like it shouldn't be that hard. I'm just trying to figure out. Yeah, okay, I see why. Or, oh no, I thought I did.
so we are trying to prove N, M dash, and LK parallel, right?
LK and M dash N. I think that might be what you
Yeah,
said.
yeah, same thing. So I'm thinking of some symmetry because uh, N is in fact a reflection of P. So if N M dash and LK is parallel to something else,
Yeah, I was thinking I could show that they're both perpendicular to FK. Or I'm sorry.
yeah, I see what you're trying to do, but uh, I think we should use some tangent or stuff because 90-degree and tangent they're like uh, I don't see a way out.
But yeah, basically I'm saying we can hide a lot of the thing, like we can hide a ton of stuff in the figure. All we need to do, the only thing we need to do, I'll even hide that. All we need to do is show that MK is perpendicular to KA.
Okay, yeah, makes sense.
And that seems like it shouldn't be that tricky, right? I just, well, so if K is the excenter and M is the point where it's a parallelogram, then we need to show MK is
Yeah,
perpendicular to KA. But we know that the angle bisector at A is perpendicular to AK. Let's see. So like we know this line is perpendicular to AK and we want to show MK is perpendicular. So we want to show they're parallel. And that seems like it should be an angle chase, I would think. Let's see.
Could we calculate angle AKC? AKC is wait a second. What was what's angle AKC? Because it must be in terms of B, and AMC is definitely angle B. So some
Yeah,
sort of
maybe. Let's see. I don't think AKC, it's not equal to angle B.
no, it's not. In
But it
terms
might
of
be,
B, if you could,
yeah, there might be a way. Hold on one second. I want to make sure that these two lines are, oh no, I'm missing something. Those two lines aren't necessarily parallel. Now I'm actually starting to question a bunch of other stuff.
the Menelaus theorem idea definitely will work because we know for the fact that it's definitely collinear, and there is a triangle we found out. So somehow that Menelaus theorem uh, is definitely
A good idea.
it's I don't know if we could do it, but it definitely has a solution through it. Like for example, in chess you see a position, but you don't find what's the right move, but you know that this position got some weakness theoretically. So
Oh
it
yeah. I think what I got hung up. No, it's not this is not necessarily a right angle. Yeah, we have to show they're parallel, but it's not
yeah.
necessarily a right angle, but it is perpendicular to the angle bisector A. So we want to show MK. Let's see. Yeah, no, it feels like it's the right idea.
But the thing is, we're not able to grasp how to find the ratio of those segments, because that will only lead to a proof of proof through Menelaus theorem.
Yeah,
So I don't. Yeah.
let's see.
Could you cut off some of the lines, because so many of lines it looks so confusing.
Let's
Like
see.
only the part you have extended, it will be a little more clean, like the extended part.
Uh,
It's okay.
but hold on a sec. I guess I don't want. Yeah, really, it's like I want to show it up to the tangency point, right? So I could do it like this.
Yeah,
Um,
this is better.
yeah. Whoops, sorry.
Once again, at what triangle you were trying to do that Menelaus theorem stuff? Because C1 and B1 are midpoints, so there is something I'm trying to see.
Yeah, I was trying to use Menelaus on triangle FKL,
FKL.
and
Uh-huh.
MN bisects it.
and KL.
Yes, or FKL. So if you look at triangle FKL, for example, that triangle, and then if you look at this line right here, cut, then AN is equal to AM, and so that's what I was thinking.
Could you name the points of tangents of the both circles? Um because the point of tangent at line segment AC. Yeah, just make any random point.
So I actually think I've solved the problem. What were you thinking?
I was thinking to find out that point of tangent to A, and then subtract it with AB1 and do something with Menela's theorem. Yeah, how did you get it?
So yeah, show me your idea. Like, you can either message me, or you can show it to Ram. But I think I have an idea that works.
Yeah, go on.
So basically, we let KL meet this line at a point. So I'm using projective geometry here, actually.
Okay.
So I'm just trying to make it look nice. So see if there's a good way to.
Yeah, this is okay.
Okay, so I let this point, let's call it P. Okay. And then, so PL and, so yeah, KL meets it at P. And then I will draw the angle bisector here. And I will let it meet it at a point, I'll call this Q. So AQ is the angle bisector. Whoops. So then AQ is perpendicular to AP. That's like a known fact, although yeah, AQ is perpendicular to AP.
Yeah.
And so the 4 points B, C, Q, and P are in harmonic conjugation.
Wait a second. PAQ. AQ is perpendicular to AP. That is correct. Then how harmonic conjugate comes here?
Yeah, so AQ is the angle bisector of BAC.
Yes.
And so whenever you have like AQ is the angle bisector of BAC.
Yeah,
And
angle bisector. BQ is to QC, AB is to AC.
yeah, exactly. So that's so yeah, PQ over PC is equal to BQ over QC, or yeah, PQ over PC is equal to BQ over QC.
PQ, PC. How did you manage to get PQ over QC?
So there's a so yeah, this is kind of
Okay. You don't need to go through the proof. If I'll get through it as a fact.
yeah, it's the second video on my channel on projective geometry.
Yeah, I'll watch it.
I think it might be 70, or no, I think it might be Yeah, I could show you what number it is. But yeah,
PQ is to QC is equal to
PQ over P.
PC is to QC, right?
Yeah.
Okay.
So that
Okay.
cross ratio is 1. And then my idea, what was my idea? Oh yeah, we can project those points through F onto line MN. I'm trying to remember. Hold on just a sec. I'm trying to remember what I was thinking.
Yeah, sure. Project through F.
Wait, so I want to show actually that P, L, A, and K are in harmonic conjugation.
Okay.
Oh yeah, that's the same idea. So actually, so there's actually a
Must
lot
be
of
some
different.
symmetry.
Yeah, there's actually a lot of harmonic conjugations here. So basically, it's also so QL bisects angle AQP, right?
QL bisects angle.
Uh,
Yeah, correct.
Actually, never mind. Not QL. CL.
It looks like the midpoint, so I thought.
Yeah, CL bisects angle ACP. So
L.
yeah, so
L bisects angle.
ACP.
Why is that?
So L is the X circle of this triangle, and the X circle is always on the angle bisector from angle AC.
Yeah.
So that's an angle bisector, and also angle LCK is 90 degrees.
LCK. Yes.
So basically, so by the theorem I just mentioned, but looked at a different way, P, A, L, and K are in harmonic conjugation.
Okay.
And then we can take those points and we can project them through point F. So I'm going to delete one of these two. So I'm going to let NL meet BC at point F. And I can take those points in harmonic conjugation, so P, A, L, and K. And then I can project them onto the line MN. So FP is parallel to MN. So P goes to the point at infinity, and then N goes to point N on the line MN, and A stays at the point A, and K would go to some point M prime. Yeah, so yeah, I see how to do it. It's just a little tricky to write out, but basically, let me write out the steps here. So K is, I'll just draw it so it's sort of way up there.
They should allow students to use this GeoGebra in IMOs.
Oh yeah,
Because yes, because we have the technology to do that, and most of the time, not most of the time, but 20% of the students still get very confused with the question. what is to how to draw, and some points coincide without any reason. So I think GeoGebra should be a thing in IMO,
Yeah, that would be fun.
maybe in future.
Okay, so I'm trying to remember what I was doing here.
You were
Oh yeah,
projecting F and
yeah. So I don't even need point two. So so CN bisects angle ACP.
CN. Yes.
All right. And then also, uh, hold on just a second. Oh no, not CN, CL. L is an excenter, so CL bisects that. And then KCL is 90.
Do you save all these solutions and questions with the figure in a file, or you just
No,
walk through?
no, I just delete them just because, yeah, it gets too many. Um,
Yeah.
so, so combining the above two, then we have A, P, K, and L are in harmonic conjugation. I'll write it like this. So KL is -1. And then we want to project through F onto line AN.
So you got two harmonic conjugates, and you are reflecting F. You got L CL bisects ACP, and I don't see at final. What is your thought process?
Yeah, so K, A, L, and P are in our harmonic conjugation.
Yeah. That is.
And so I want to project those 4 points through F onto the line MN. So,
Okay.
so first I'm going to write out what we knew about these being a parallelogram. So, So okay, so now I'm going to project through F. P, and that's equal to, so K would go to okay. But so this means basically this means that FK intersects MN at point M.
To be honest, I'm not that familiar with projective geometry, although I have some basic ideas, but still, I'm learning through Evan, so it's quite hard for me.
Yeah,
I'll
it
watch
takes,
the recording and maybe get some more intuition.
yeah. It's kind of, yeah, I'm sorry. Like I would try to explain in more detail, but it's hard for me to kind of multitask a little bit, typing. But
Yeah, I see.
yeah, I can talk to you about it offline. Because yeah, projective geometry is my favorite tool.
Yeah. Yeah, my grandfather used to be a civil engineer. He was quite big in our state. So he used to also like geometry and he used to do all those things, and that's where I got my passion for mathematics. So he was really good at these stuffs at projective geometry and things.
ah, but then this basically solves the problem because that means Kn, Ln, and Bc meet at F. But you said he was an engineer?
No, yes, my grandfather was a civil engineer.
Interesting. All right, well, I'm going to stop the recording for today, but I want to
Yeah.
thank all the participants for joining and participating in solving the problems.
Please
I think we
subscribe.
and subscribe. Yeah, I think we got through 7 problems today, so I think that might have been more
Yeah.
than we've ever.
How many subscribers are we in? It's like 1,000. We're close to 1,000, right?
Not quite yet. I think it's 550 or around that maybe. But yeah, hopefully someday it'll get up to that.
Yeah.
So thanks everyone for watching. So I'm going to stop recording now, but I will see you next time.